Okay, hello everybody to this week's ISGC seminar talk. Today's speaker is Béatrice Bonga. She did her PhD in 2017 at the Pennsylvania State University, and now she's an assistant professor at Radboud University since 2020, and she will talk to us about quasi-normal modes on black hole horizons. Thank you very much, Béatrice, for agreeing to give this talk. The stage is yours.
Thank you very much, Torben. I'm very happy to be here. I'm excited to talk about this topic, which is something very close to my heart. So as all of you probably have noticed, we live in the area of gravitational waves. Right? And I think gravitational waves make lots of things possible, but two things that for me as a theorist are particularly nice about them are one, the test of gravity that they allow, in particular in the strong and dynamical regime, right? Because if we see the two black holes that go around each other, clearly this is, strong field and also highly dynamical, right? I mean, the closer the merger, their velocities can go, as close to about 90% the speed of light. But there's something else that, sort of recently popped up that also is quite exciting because gravitational waves make the test of the nonlinear nature of gravity possible. So as a theorist, typically, it's very easy to, write down the linear part of your signal and then introduce nonlinear corrections. Right? That's how we often operate. But if you do an observation, right, you typically get the full shebang, right? The linear piece and the nonlinear piece together. There's no natural split. But as it turns out, in this final part of the gravitational wave signal, that, in fact, that split naturally occurs. And that's where we can, without much work, see these nonlinear parts very cleanly. So to zoom in on that part of the signal, I thought let's do a one-on-one on the whole signal, right? So generically, right, if we look at the gravitational wave, we have something that we call the in spiral, where the frequency changes, but the amplitude doesn't change much. And we use post-Newtonian methods to describe that. Then we have this merger signal. It's complicated. We don't really have good analytic tools in that regime. So we use numerical relativity. And then in the final phase, the two black holes have merged and form a highly deformed black hole that rings down gravitational waves and settles down to a standard, curved black hole. And in that process, it emits something that we call QNMs, or quasi-normal modes. And these are the, play a key role for what I'll be talking about today. So what are quasi-normal modes? So if you've never heard of them, you can think of a simpler setting, or actually more complicated setting. We'll see that in a bit, right? Think of a bell, right? If I hit the bell with a hammer, right, some notes come out. The tones that you hear are determined by the properties of the bell, right? For instance, if I have a bigger bell, you'll hear lower tones, a smaller bell, higher tones, etc. Similarly, right, you have to think about the shape of the bell, the material the bell is made out of. All these things determine what you'll hear. And it does not really matter that much with what you hit the bell. So for instance, right, if you have Ramen Hood hitting with an arrow, you also get similar tones, right? You might excite different modes, but the frequencies that you can excite, right, and that you might hear are completely determined by the properties of the bell. Now, the same is true for black holes. So if you hit a bell, or a black hole, right, perturb it, it will also emit specific frequencies. And these frequencies we call quasi-normal modes. And in fact, the black holes are the simplest possible bells that we have in our universe. Right? Because in order to describe all these frequencies that bells emit, right, we need to know all these complicated properties. But for a black hole, all these frequencies can be completely derived from just knowing the key properties of a black hole, right, which are just the mass and the spin. So in that sense, black holes are the simplest bells that we have in our universe. Now, what is the mathematical description of them? Right, typically, right, we analyze our gravitational wave signal, we decompose it into a plus and cross polarization, and we can, if we work on some black hole space-time background, we can decompose it in a time radial part and an angular part, where this angular part are modeled by the spin-weighted circle harmonics. And this time radial part, the leading order bit is proportional to 1 over r. There will be first corrections, but 1 over r. And then this part described by quasi-normal mode. So what do we see here? Well, there we have those frequencies, right, that I talked about. These frequencies are complex, right, because they have to describe the fact that the signal, as you remember, right, it is a decaying sinusoid. So we need to include that decay. So that's here. And then we have the amplitude and the phase. Now, the cool thing, right, the frequency is completely determined by the mass and the spin of your black hole. And the amplitude and the phase are more complex in the sense that they depend on the details of the hammer, right? So what is perturbing the black hole? And if you want, of course, right, in nature, we're not going around and hitting black holes with hammers, right? But in a merger, right, you can think of, say, the lighter black hole as being the hammer of the small of the more massive black hole. So the amplitude and phases are typically quite complicated to determine, right? Because they are set by the merger dynamics. And that is exactly a regime that we don't really have a good handle on. But these phases we know how to, or the frequencies we know how to compute very well. And these, as I said, right, these frequencies are real and imaginary, right? A real and imaginary part. The real part we just called the typical frequency, and the imaginary part is directly proportional or inversely proportional to the damping time. Now, there are a whole bunch of labels. I think I have to just quickly explain them to you. So will be helpful to understand the rest of the talk. Right? There's 3 integers, these labels L, M, and N. L just runs from 2, 3, etc. And the L comes, of course, from that circular harmonic decomposition. Similarly, M will be from minus L to L. And then N is an additional index that denotes which the overtone you're talking about. Right? So for instance, right, I can excite a specific mode, and you can have, right, the fundamental tone, right, the fundamental frequency, or higher ones, right, when you cross the horizontal axis multiple times. Very similar, right, to say the overtones of a violin string. Now, the very cool thing about the whole, these quasi-normal mode frequencies for a long time, and I think still is actually, in fact, is something that we call black hole spectroscopy. So what is the idea behind that? Well, right, if you measure a single QNM frequency, right, you get 2 numbers out. From these 2 numbers, you can then determine the mass and the spin of your black hole. Great. Now imagine that you can, in fact, measure 2 frequencies. You can do the same thing with the other frequency, measure the mass and the spin. But then it better be, of course, that the mass and the spin that you get from your second frequency is consistent with the first one. Right? So this gives you very interesting, non-trivial checks on your Kerr spacetime. And that's why lots of people have been looking into this since about the 70s, and there are many, many interesting results. Now, what is recently new is something that is thinking about going beyond linear order. Because I said these frequencies we can compute very well, and that's true, but we typically do that within linear perturbation theory. And as I mentioned before, right, the phases and the amplitudes, at least in data analysis, they're typically treated as free parameters because it's difficult to determine them from analytic computations. But if we now go to the next order, right, to second order, something very neat happens, right? So at second order, we can get a new set of frequencies, which I'll call quadratic frequencies, because they come from second order, which you can get by taking the sums or differences, if you want, of the linear modes. Now, why do I say this is cool, right? This means that if I see such a quadratic frequency, I know it has to come from second order, right? Because the frequency space is sparse. So if you see this frequency, you know for sure it has to come from second order. So this is a very clean signal in that sense. Moreover, what's also cool is that the phase and the amplitude in principle are completely determined from black hole perturbation theory. At linear order, we have to treat the phase and the amplitude as free parameters, but at second order, this is something completely computable, right? And it should just depend on the mass and the spin of the black hole. And of course, the linear amplitudes, right? But once you know them, you know the quadratic amplitudes. Now, this was long thought, and there will be a little bit of a twist later on to this story, but that at least got me very excited about going to the next order. But then, of course, right, one should always be a little bit skeptical, right? You could say, well, it's already difficult to see a single mode at linear order. If the amplitude is small, right, then surely the quadratic amplitude will also be small. And that's a fair point. However, there's some very cool results from two different groups, actually, about 3 summers ago. Here I show you the plot from one of the set of papers, but I could have easily taken the other set of papers. And they showed the following. So it's a busy plot, so I'll take you through it slowly. On the real or the horizontal axis, we see, right, the real part of the frequency. And on the imaginary axis, or sorry, on the, you hear me talk, right? On the vertical axis, you see the imaginary part of the frequency. Now, what they've done here, right? They didn't look at actual data, because currently with LIGO Virgo, we only see 1 or possibly 2 modes. But this is looking at numerical simulations of black hole binaries and analyzing them and see if we can fit them with these quasi-normal mode signals. So this, of course, only applies to that final part of the merger, right? Or in fact, actually post-merger, right? In this ring-down phase. And what they've done here, they focused on the L equals 4 mode. They looked at the L equals 4 mode, and they first fitted it with the fundamental mode, so the 440 mode. Nice, good fit, great. Then they looked at the next mode to include. So they found that they needed to include the first overtone, so the 441. But then they said, okay, let's now ask the data which extra frequency does the data prefer. And they did this, sort of by computing the mismatch between your model and the data at each point in this frequency plane. And of course, right, if you want to have a good fit, you want your mismatch to be as low as possible. So what they found is, right, that the best fit is somewhere here in this dark blue region, which is exactly where you have this mode, which is a mode, right, the green cross, which is exactly a mode predicted from second order in perturbation theory. And it is not what one might have thought previously, the next overtone, so the 442, right, which is way up here. So this is pretty neat. Of course, right, if you find the frequency, you should do something more, right? It should not just be that you get the right frequency, but you should also have that the amplitudes indeed satisfy the relation that you expected them to have, right? So what you see here on the horizontal axis is indeed the linear parent amplitude. And if I now look at the associated quadratic amplitude, you see indeed this nice quadratic relationship. And here the dots are for like various numerical simulations. And it's not trivial to get something quadratic, right? Because for instance, if I also look at, say, the fundamental mode, the 440, there's obviously no such correlation between these two modes. So this is nice and convincing. But then something puzzling happened, right? Because then initially, right, all these numerical groups found these results. And originally, there were no results yet in second order perturbation theory, because, I mean, fair point, right? As a community, we're all busy and we should focus our efforts on what's the most relevant and most important. And of course, no one really thought that, second order perturbation theory would be useful. So my apologies. So after these interesting numerical results came out, various groups started to compute this in second order perturbation theory, but different groups found different values, which is weird. And none of them agreed with numerical relativity, which is also weird, right? Of course, one could have said, well, if you don't agree with numerical relativity, maybe that's because, right, in numerical relativity, there should be maybe higher nonlinear effects also important, or other, right, mode coupling or other things. So that might have not been too worrisome. But the fact that you find different results from the same analytic computation, that, of course, is not too good. So this was very confusing. But we also decided to do that exact same computation. And we realized, in fact, that all the different groups actually did their computation correctly, but they made different assumptions, or they realized they missed a key assumption. So why is this happening? Well, right, at linear order, essentially to describe these quasi-normal modes, what you do is you have the Tucholsky operator, which I'll just denote by some O, acting on your psi4 scalar. So this is a Newman-Penrose scalar. If you don't know what it is, you can just think of it as the second time derivative of your gravitational wave form. Now, at linear order, what we typically do, right, we decompose this into the spherical harmonics, right, that I showed you before, some exponential time piece and a radial piece. Now, at second order, you get exactly the same equation on the left-hand side, except, of course, that you now act on the second order psi4, but the Tucholsky operator is exactly the same operator. But on the right-hand side, now you have a source, right, which is, composed of psi4 terms at linear order squared. And of course, background terms. So there could be like mass and spin and radial additional dependence, etc. Now, if I also decompose my field at second order into these spherical harmonics, right, and I do the same kind of decomposition, then, roughly speaking, right, what you get at second order should look like this, right? So I should get some quadratic amplitude, some exponential that I have up here, and then that is proportional to these the linear amplitude squared, and again this exponential with the frequencies there, right? And I get two frequencies, and that's why, right, the quadratic frequency can be twice the linear frequency. Of course, we're interested in this relation, right? So what is this amplitude that I get from these linear pieces? Now, as it turns out, in fact, actually, what wasn't realized is that the source term is a little bit more complicated than just this. Than just psi, right? Because it turns out that you have psi, but there's also another term that is psi with the complex conjugate of psi. And you may say, okay, that's getting a bit technical and boring, but wait for it. There is a nice, physical interpretation to all of it. So this means, right, because of that second term, that there are in fact two ways to obtain 2 times the linear frequency at second order. Right? Because I can have this term, right, that I used to look at, but I can also have this term with something, with the complex conjugate of something that we call the mirror mode. So here, this is the typical regular mode, and this is a mirror mode with the -2, and they satisfy this particular relation. So if I take the star of this mirror mode, I get the usual regular mode with a minus sign. And because of the additional minus sign in here, this is why this gives me exactly, again, 2 times omega 220 if that's the mode that you're looking at. As a result, if I now write down psi4 at second order, there are 2 terms contributing, right? The 2 from the regular modes and 1 from this cross product with the regular and the mirror mode. So if I now take the ratio of this quadratic frequency, or of this quadratic field, quadratic amplitude to the linear ones, just the usual regular ones, there are 2 terms contributing, right? The A220 and the B220 multiplied by this term. Now this term, right, is exactly this ratio of the mirror mode to your regular mode, and that has a nice direct link to the ratio of the odd and even modes. You may say, okay, that's still a bit technical. I don't know what you mean by even and odd, but if you want, you can just think of it in this way. This is directly related to up-down symmetry. So if you have, for instance, 2 black holes colliding in the plane, right? You have exact, or I mean, okay, depending on some, say 2 non-rotating black holes, you have exact up-down symmetry. And as a result, you do not excite any of the odd modes. In cases where you say have precession or things like that, you do excite the odd modes. So in certain cases, like this term may not contribute at all, and in other cases, it does contribute. So after all, the ratio, this ratio that people looked at, is in fact the initial data dependent. It's not independent as was long thought. So doesn't just depend on the mass and the spin of the final black hole, but it also depends on some of the properties of the progenitor system, and in particular, how much up-down symmetry there was. And this was very nice because this reconciled all the previous results in the literature. So this again is also a bit of a busy plot, but here what I show on the horizontal axis is essentially this ratio of odd to even modes, at the real part of it, and on the vertical axis, the imaginary part of it. And the color coding tells you how much this ratio is that I showed you before. So, and now what we see is, for instance, there were two results, analytic results, the one by Ma up here and the one by Bucchiotti right here in the middle. And we recover exactly the same values that they had, right? So if we look at our color coding, you find that this is, for instance, 0.138 or something, and that's exactly what Ma also finds. Bucchiotti finds something else, and we also agree exactly with that value if we use, in fact, that there are no odd modes. And that's, in fact, actually something that they had assumed from the start. So here you see nicely how this can reconcile these different results. Then there are a few other interesting results. For instance, these sort of like more these regions instead of these dots, they refer to the results from numerical relativity. And we seem to be somewhat, well, I mean, not inconsistent, but they seem to be right here. So this is very nice. Of course, there's one big caveat. Our computation, so our color coding, assumes Schwarzschild as a background. So we, in fact, have not done the computation for Kerr yet. This is something that we're still pursuing. So in some sense, we are definitely allowed to compare with Ma and Bucchiotti because we compared with our Schwarzschild results, but the comparison with numerical relativity is, of course, a little bit, one should not really do that, right? In fact, because their final black holes do have spin, typically. Now, here is an example where, in fact, we are allowed to compare directly. And because this is, here we are comparing to only numerical simulations, because there were no other analytic results to compare with. And here you see that in this case, right, this is a head-on merger. So the final result is a non-spinning black hole. So this is a legit comparison. And we would have expected, right, because of the head-on merger, that they should not have had any odd modes, right? So we would have expected, in fact, that their results should have been, centered around our origin, but they're not. So this is something interesting, and we, in fact, think that either, their error bars are not as small as they think they are, or they could actually improve their analysis by implementing the fact, right, that they don't have any odd modes, and that should change the results. But again, this is something to still, this is something that's still under discussion. Now, I'm finally getting to the second part of the title of my talk, right? I said quasi-normal modes on black hole horizons. So based on all of these, exciting developments, right? All of this typically, right, when people do, and they do these fittings, they look at the gravitational wave signal very far away at, null infinity, or at least, in the radiation zone. So I was curious and wondered, can we actually also model the horizon with quasi-normal modes? So the angel part in me said, well, great idea, right? The horizon should be more non-linear, but nothing too crazy. So it should, in fact, actually be easier also to find these quadratic quasi-normal modes, and this will be very nice. The devil part in me said, well, don't even bother, right? Because the horizon is clearly in a strong field regime. So it's hopeless to even try and fit this with any QNM description. Lucky I have some brave student that took on this challenge, and I think the results are very nice. But first off, you may wonder, okay, why should I care about the black hole horizon? And to that, my answer is the following. So I am after something that I'll call not black hole spectroscopy, but black hole tomography. Right, what we typically do within the gravitational wave community, we focus very much on constructing waveforms and modeling how our gravitational wave signal will look here on Earth, right? So say for the Einstein telescope or LISA, or currently LIGO Virgo. This is what most of our efforts go to. But I think that's, that should not be enough, right? That should not be the end of the story, right? Because just as with in all of astronomy, right? If we just see, say, some gamma ray in our detector, it's not, I mean, it's great, but it's not too exciting. But if you can relate that gamma ray to an interesting source and learn about the key properties of the source, right? For instance, that, if that gamma ray came from a binary neutron star merger, and you can learn that most of the gold in our universe is actually made in those kind of mergers, then it becomes very interesting. So, just modeling the signal that we see at Earth it's not enough, right? Ultimately, we want to use this signal to tell us something about the objects or that emit these signals. And that is the same for black holes. So I want to, make this connection and say, okay, if we see something here on Earth, what does that mean for what the black hole is doing? For instance, if I see some quasi-normal modes, right? Ooh, this is going, yeah, I'm not great with creating animations, but this was done with the help of my student, but I should have slowed it down. Apologies. Essentially, if I see a gravitational wave at infinity, right, or on Earth here, I want to be able to tell how does the shape of the black hole change, right? What happens to it, right? You see it wobbling down a bit. That is my goal. Now, of course, ultimately, to make this connection, one would like to do this fully non-linearly. That's very hard. So one can do two things, right? Pursue this approach in perturbation theory, which is something that we've done. But for the purpose of this talk, I'm going to do something else. I'm going to just focus on the black hole itself, on the horizon, and see if I can learn something from it in the fully nonlinear regime. So there it goes again. Great. Let me see. Yes. So what did I do? Well, we analyzed two sets of numerical simulations from the Einstein toolkit, where the resulting black hole, right, is a head-on collision of two non-rotating black holes. The resulting black hole is also non-rotating. So these simulations are completely axisymmetric, and that's nice because it's easier to implement, but it also means that if we look at the quasi-normal modes, they're only m equals 0 modes. You don't excite any of the other m modes. Now, so also in some of the plots, you see then some QNMs with only two labels. If a label is missing, right? So if you don't see 3 integers, but only 2, that means that I've just suppressed the m equals 0 part. Now, the nice thing about these simulations is that they have very high resolution near the horizon. So we can now go and do exactly sort of the same thing that these other people did 3 summers ago, where they analyzed the gravitational wave signal all the way near infinity and fitted it with all kinds of QNMs. We can do this now at the horizon. The downside is, of course, right, we have the resolution is very good close to the horizon, but it's very poor far away. So I cannot do the same analysis at the horizon and infinity at the same time. I just have to focus only on the horizon. And we use 2 different sets of simulations. So essentially one that we call the unboosted ones, intuitively meaning that we looked at different masses, so different masses for the black holes, but their initial velocity is 0, so they don't get any boost. And we had a set of boosted ones where the masses are the same and they have an equal but opposite boost going at each other. Now that's nice because, as it turns out, right, as you can also maybe imagine from particle physics, if you have boost, these linear amplitudes will be bigger that you excite, and in fact they're 10 times bigger. So it's a little bit easier to work with. The signal is a bit cleaner in that sense. Now, what am I going to look at the horizon? Here you see a typical plot of the evolution of a horizon, where, of course, as in GR, time goes up. And here you see that the horizon, as the quasi-normal modes are absorbed by the black hole, the horizon is growing. And that's what you see here. And then at some point, right, the system is settled down to the stationary state, and nothing really changes anymore. And you get this isolated horizon. Now, in the regime where the horizon is still changing and growing, that's where I'm going to focus on trying to describe this horizon. And the key property that I'm looking at, or that I'll show you the results for, will be the shear of this outgoing null normal. We've done, in fact, also the analysis for multiple moments and other things. They're all qualitatively similar. But the shear is I think the most intuitive thing to look at, as that is very closely analogous to, say, your gravitational waveform at infinity. Now, there's one thing that I should be honest about, and I think this is important to make this disclaimer, and that has to do with the choice of time, right? Because your choice of time is important, right? If I change my definition of time, I change what I mean by frequency. So at the horizon, we should be very careful and think about, well, what time are we in fact using, right? We did not have a good theoretical framework to decide what time to use, right? Because clearly these numerical simulations, right, their initial data are set way before you have a single black hole, right? There are two black holes far away. So the time that you have is clearly should have nothing to do with the typical Schwarzschild time, right, that we use to compute the frequencies in black hole perturbation theory. So it would be nice to sort of come up with a deeper understanding of what time to use. We just said, okay, let's close our eyes and jump and see what we can get out. And we decided to use the simulation time. Now, of course, the issue at infinity is in some sense the same, right? Because also there, they don't have, in some sense, a strong justification for using the simulation time. Although, of course, at infinity, one can say, well, you always approximate something asymptotically flat. So all reasonable time choices will have to agree with the Schwarzschild time. At the horizon, we cannot make that argument. Now, there's one thing that is better at the horizon that you don't have at infinity. And that is that we have a very good handle on the changes of the mass, or, well, I showed a plot, the changes of the area. So here you see how the mass changes once the common horizon has formed. And you see that for the boosted simulations, the changes is a bit larger than for the unboosted ones. But this is nice, right? Because this at least gives us some sort of handle to say, okay, this is what we consider like a valid time for our ring down analysis to start. This is a time where we can at least say, well, if the mass change is less than so much percent, we used in the case of 1%, we said, okay, if the mass change is less than 1%, it is valid to use black hole perturbation theory, and we should be able to understand that. Of course, the 1% is somewhat arbitrary, right? One could have said, 2% or 0.1%. That one can debate, but at least, right, we have some understanding of what's going on. At infinity, you do not have that. So we decided on this cut of 1%, and for one of the simulations, that meant that the ring down, right, the most stringent one that's up here, we said, okay, the ring down time will be from like 8.2 m onwards. And we decided to use that same time for all the simulations, so we didn't have to deal with different times and all of that. But in principle, right, we could have implemented this this thing for 1% or less. This is just to say that in some of the simulations, right, that will analyze the mass, in fact, changes even less than 1%. Good, so let's now look at the result. So here in this plot is essentially exactly the same plot that I showed you before from the group that done the analysis at infinity, but now at the horizon. So here we look at the L=2 mode, and we have already, extracted the fundamental mode, the 2, 0, 0, and its first overtone, the 2, 0, 1. And then we ask the data, okay, what is the best fit frequency that you seem to prefer? And what you see, right, this is again the mismatch, right? The best or the most optimal frequencies are down here, right? With the 2, 0 cross 2, 0 or the 2, 1 cross 2, 0. Sorry, still recovering from a cold. So the upshot is, right, clearly also at the horizon, we seem to prefer quadratic frequencies. And over, other, say, linear overtones, for instance, right? Here would be another overtone. That's not the one that we find. And if we then look at the amplitude relation, that's also a very nice behavior that we expect. So here you don't see a quadratic line, but you see a linear one. And that has to do with the fact that, right, I already put the quadratic amplitude here on the horizontal axis. So we find indeed that there's this nice quadratic relationship for the boosted and the unboosted cases. There's one thing though that's a bit weird, and that we were puzzled by at the time, and that I think now we have an explanation for. Because at the time we analyzed the boosted and the unboosted case separately, and then we find something, if you look very carefully, right, the slope of both of these is very different. And that's weird, right? Why is that slope different, right? If, you know, the lower was, right, this slope should really only depend on the mass and the spin of your final black hole. And the spin of all of our black holes was, the final black hole was 0, right? Because we were looking at a Schwarzschild black hole. So these two numbers, right, and the mass of all of these also, I should say, right, was normalized to 1. So these numbers should have been the same. And we were very confused by this. Ultimately, we decided to just say, okay, we actually don't know why the two are different, but here is the result. Now I think actually the reason for this, and we're still testing this, but the reason for this will have to do with this up-down symmetry, right? Because in the boosted case, you have up-down symmetry, right? So you're not exciting any odd modes. But in the unboosted case, right, I don't have this up-down symmetry, right? Because one of the masses is larger than the other ones. So I am exciting odd and even modes. And this might be exactly the explanation for why these slopes will be different. Now, to actually test that, right, well, what you should do, right, is compare numerical relativity to the predictions from black hole perturbation theory. But that is always challenging, right? As you know, if you've ever tried doing that, that is not non-trivial. So the results for black hole perturbation theory we already have, but the comparison with NR is tricky because of several issues, right? The location. So in black hole perturbation theory, right, we work with the domain that we compute things is all the way from the event horizon to infinity. But in the numerical simulations, we looked at the apparent horizon. The apparent horizon is inside the event horizon. So we cannot use the predictions from black hole perturbation theory directly to look at these the predictions or the results that we have at the apparent horizon. Then something else, which is just sort of how the code was evolved, right? But we looked at, in the numerical simulations, at the shear modes, as this was easily implemented. But then black hole perturbation one more naturally works with psi naught on the horizon. At infinity, you work with psi 4. On the horizon, you work with psi naught. And then, of course, anytime, right, you do a comparison, it's nice if you're in the same gauge. And that is really hard to say because at black hole perturbation theory, you work with an ingoing radiation gauge if you study things at the horizon. Whereas, right, in NR, you choose a gauge that is motivated, right, by this 3+1 split. And I've been told, no, I don't do these simulations, but that is the gauge that they're using, right? And it has no, a priori, really nothing to do with this ingoing radiation gauge. Now, how are we overcoming these issues? Well, I have a student who has nicely taken or looked at these problems and said, okay, let's take our NR simulations and not look at the apparent horizon, but find the event horizon. So he implemented an event horizon finder, which is what you do. You take the final time, you look at your final slice, you take that apparent horizon as an initial guess for your event horizon and then use ray tracing back. And he's also implemented a new way to compute the psi naught, so we don't have to work with the shears, and is currently analyzing all the QNMs. And I'm very optimistic that this will hopefully explain this difference between the two, the boosted and the unboosted case. Now let me wrap up here. So as I hopefully convinced you, that these quasi-normal modes can be used to very cleanly probe the nonlinearities in general relativity. And this particular ratio of these quadratic amplitudes to these linear parent modes is not initial data independent, but it depends on initial data, but luckily only in a very specific way, right? Through this ratio of odd to even modes. Now we've seen that these quadratic quasi-normal modes can also be extracted at black hole horizons, and the comparison with black hole perturbation theory is still ongoing. And this is something I haven't mentioned, but I think the future is very bright because observations of quadratic modes, which is not work that I've done, but it's extremely likely with the Einstein telescope and LISA, as there are by now different forecasts from various groups that really seem to indicate that this will be essential. In fact, for some of the LISA sources, I've seen that it will be essential to not just include one quadratic mode, but two. And this will be the minimum number of modes. And so there might be even more that we'll see. So I think this is very exciting, and lots of things are happening. And I hope that new things will come out soon. I'm happy to take any questions.
Thank you, Beatrice, for this really nice talk. Are there questions? Okay, there's one question in the chat. I just read it. What is your estimate for the frequency range of these modes?
So it's very easy to get the frequencies of these extra quadratic modes. You should just take the linear ones and look at the sum of them. So for instance, right in this plot, right here, if you, for instance, look at the 2001, typically for the quasi-normal mode merger, the 2201 is the more interesting one. But if you look at the head-on, it's the 2001 that's summoned. And you see this is a typical, linear frequency, and this will be an overtone, the next overtone, etc. And here you find the frequencies from the quadratic order. So right, you just double the result. And there's also maybe something nice. I did not mention this explicitly, but if you then look at also this, you see that the overtones, right, have a specific imaginary part. And if you remember, right, the imaginary part is inversely proportional to the decay time. So these quadratic frequencies actually have have a smaller imaginary part, so a larger decay time. So in fact, these overtones decay very rapidly, but these quadratic frequencies decay less rapidly. So you might actually, indeed, that's also why you can pick them up in the data. Let me see. Okay. Maybe actually the question was about the linear frequencies. So for the linear frequencies, indeed, these are extremely nicely tabulated, also on different websites. There are different packages. You can, for instance, look at there's a nice open source package in Python developed by Leo Stein. It's also, there are some implementations in Mathematica by various groups. If you look at the Black Hole Perturbation Toolkit website. So the linear part is like pretty solid. And for that also, I mean, as I said, right, the quadratic ones are also easy to get. You're welcome.
Okay, are there other questions? I see Jay already turned on his camera, which usually means he has a question.
Oh yes, I do. Thank you, Beatrice, for a very nice talk. So my question is about like in quasi-normal mode community, in particular, if like we want to extract those modes from real data, we have to be careful with, for example, these nonlinear modes contributions and also the contributions from overtones. Like recently, many people are discussing how those different overtones will contribute to the black hole spectroscopy program. So my question is about, in your opinion, how can we distinguish the contributions from these nonlinear contributions, nonlinear modes, and the higher overtones?
Yeah, I think this is a great question. So I think, well, what we see at the horizon, for instance, in fact, so here I showed you the results for the alkyls 2 mode, where, for instance, if I look at the alkyls 4 mode or the alkyls 6 mode, we find that we get the fundamental frequency and then 2 quadratic ones. We don't find any evidence for overtones. So, okay, no one can say, well, horizon, more non-linearities, etc. I think ultimately the best way to do it and answer this question is to develop better theory, because what currently, right, is sort of leading debate is, well, let's look at the numerical simulations, let's fit them, and let's see what comes out of them, right? And then you get different communities arguing about, you know, whether the fit is good or not. But the best thing forward for me would be to actually get analytic predictions for the amplitudes of the different modes, right? That would be the ultimate way forward. And I think there are some sort of encouraging results actually from the Selfforce community that are building a full in-spiral merger ringdown signal where they are able to do this. Now, of course, it's still, you know, in its infancies and it's not, you know, accurate enough yet, et cetera, but the results are fairly promising, even if you compare, you know, at least by eye, right? Their waveform model with, say, a waveform, full nonlinear waveform in a mass ratio from 1 to 10, it does extremely well. So that would be my take on it. And of course, right, we should always make sure that, right, when we do these kind of fits, we, you know, things make sense, right? So these amplitudes should be stable, et cetera, right? We should not violate the assumptions that go into the model.
Thank you.
But it's indeed, it's a super hard problem, especially if you work with real data.
Yeah, of course, yeah.
I think this is also the reason, right? I think there's one event where multiple groups have claimed to have seen 2 frequencies already, but no one seems to agree on which 2 frequencies.
Yeah, exactly.
So everyone agrees on like the fundamental tone, but not the additional one.
Yeah.
And I think that just has to do with the fact that it's very delicate. But, you know, I think it can all be done, and it just means that yeah, that there's something for us theorists to do. Oh, I see another question in the chat. Let me see. Good. So why do I deal with gauge issues? Oh, great. There's a question. Why do I deal with gauge issues since the wild scalars are not gauge invariant anymore at second order? Good. Yeah. So this is something that's very subtle. Well, subtle. So at linear order, right? At least within perturbation theory, these wild scalars, they're gauge invariant. So it's in that sense a nice quantity to work with. At second order, they're no longer gauge invariant. However, the cool thing is, or at least near infinity, you can show that in any asymptotically flat gauge, right? So this includes many different gauges, right? But in any asymptotically flat gauge, the differences between psi4 at second order and some other psi4 at second order in another gauge, right, will decay faster than 1/r. So will decay as 1/r squared. So that means that still, if you are within this large class of gauges, it is still reasonable to compare your gauge quantity with another gauge quantity, because you know that the difference will have to decay faster than 1/r squared. So that's why I think it is, in fact, actually important to think about gauge and all that. Now, at the horizon, of course, yes. Okay, thanks. I meant more at the horizon. Yeah, so at the horizon, this is more delicate, because there, indeed, you don't really know what gauge you're in, and you cannot really, well, at the horizon, you don't really have the arguments that you can say, well, the gauge, that the differences between different gauges decays as 1/r squared, right? I mean, even if it did, that would not be a meaningful, or would not be helpful. So for that, we're currently also making sure that we're testing things, that the quantities that we work with at the horizon, and the way we extract them actually have the similar properties than the gauges that we've implemented for the black hole perturbation theory. Because ultimately, I mean, you have to think about these questions, because otherwise you might compare just random numbers with random numbers. But yeah, no, great question. Thank you for this technical point.
Any other questions? Maybe I have one. Basically, what if I mean, before supermassive black holes, we have on one hand the shadow observations, and on the other hand, we may get also some excitations from the quasi-normal modes when we have, for example, infalling gravitational waves. I never looked into it, but I know there's some, I think there was some relation. I think Cheo mentioned that once. Do you think
Yeah.
it would be quite a unique test when one has the quasi-normal modes, and in addition, one has light propagation, for example, in a plasma where we have a dispersion relation of the photons depending on the photon energy? Will this maybe help us at some point to much better probe gravity in the strong field regime?
Yeah, it would be super nice to have something like this. I don't think anytime you have more data from the same system, right, it helps you to do more stringent tests. Now, I find it difficult to imagine a system where we see the quasi-normal modes from something like that and get the light out, right? Because typically the right, so to see these quasi-normal modes in supermassive black holes, for instance, right, you have to look at them at LISA, because you can just look at the frequency and they fall exactly in the LISA band. Now, that means also LISA is very sensitive typically, right, to things far out. So these black holes are at high redshift. So even if they had somehow some disk or something around them, it would be very difficult to see that, right, with electromagnetic observations. On top of the fact, right, that one would have to understand very well, what the disk does exactly during this highly dynamical regime to get, something out. Unless you want to talk about the disk after the supermassive black hole has settled down and still has a disk. But anyhow, just to say, I don't think we have understood in any sense very well what happens to a disk if I have two black holes merging, et cetera, et cetera. I think that would be very tricky. But I mean, ultimately, yeah, anytime you have more data, it is better.
Thanks.
The nice thing, or the part that I like about this part is typically, okay, modulo, of course, all the technical details, but it is a kind of a clean signal, right? This gravitational wave signal is a clean signal. There's not much astrophysical assumptions that go into it. It's fairly well understood. This nonlinear part is also easy to extract. I don't have to do crazy fitting or something to tell me that this isn't linear, that's nonlinear, etc. So this part I really like about this problem.
Thanks. There's another question, I think, in the chat. Oh, no, it's not a question. So are there other questions? If not, maybe we can end the official part here and